Hi class, and welcome to the lecture on Unit 3.2, which we're going to learn how to write ionic formulas and how to name them. And so being able to go back between formulas and names and go from names to formulas is super important for chemistry. And so we're going to start with ionic compounds. And so we're initially going to talk about what is a binary compound. And binary compounds, all they are compounds made up of two elements. And so these are chemically combined, and they're going to be in empirical formulas, which means if I were to define an empirical formula, all that is a whole number ratio and it's going to be the most simplified. Meaning, if we take water, for example, if we were to write H2O, this is in a whole ratio of 2 hydrogens per 1 oxygen, and it's the simplest form. Versus, if I were to write H4O2, we can actually divide the amount of atoms by 2. And if we do that, we get H2O. So think of this as a 4:2 ratio over here. And so that's not the most simplified. So water's empirical formula is H2O. And so what's important to note is that these atoms combine in a ratio such that their charges add up to 0. So these binary compounds are going to be made up of cations and anions, meaning they're going to be made up of positively charged ions and negatively charged ions. And so when you add them up, the charges better equal out to 0. And so when we're writing these, we write the cation or the positively charged first, and then we write anion or negatively charged. And so when we are writing out these formulas, we do not write the number 1. So just how we didn't write 1 for our example with water, we didn't write H2O1. We don't need the 1, we just leave the 1 out. It is assumed if there is no digit there. And so this first table here, I'm saying let X designate a metal or a positively charged ion, and Y would be our nonmetal, typically negative. And so here are some examples. If we have something that is a +1 combining with a Y1, we just need a 1-to-1 ratio for their charge to add up to 0 already. This will be the same for anything that has equal charges for both the plus and the minus. So if it's 2 or 3, they already add up to 0, so you just need 1 of each. Then, once we start getting things with differing charges, if we have x equals +2, it'll take 2 y's if they're only -1 to cancel out the +2 charge. And so how we would write that in our formula is xy2. This is the same for if we have a x +3. Then we're going to need 3 y's with a -1 charge to cancel out the +3. Because what this means is that the overall charge from x is +3. Then we have 3 -1 charges. And if we add up those together, they equal 0. Now what happens if we skip down here to +2 and -3? Well, now we do what's called finding the common denominator, which shouldn't be a new term for you guys. But we need to figure out a common number between the two, that's the lowest combination, that we can cancel out the charges for each other. And so for 2 and 3, the lowest number would be 6. So how many x's would it take to get to be +6? Well, 3 times +2 is equal to +6. And then how many will equal 6 for -3? We need 2 -3 charged. That gives us 0. So when we write it into our formula, we get x3, y2. And what's a cool thing to point out about this is that the number of atoms in the formula are just the charges of the opposite one. So there are 3 x's in our formula, and the charge on y is -3. Where there's 2 y's in our formula here, and the charge on x is +2. So they're just flip-flopping their charges and using them as the number of atoms. Look at the one below. When you have +3 and -2, now you have 2 x's and 3 y's. So something to point out when you have odd numbers like that. But it also works for moving back up, even looking at this x1 and y3. They just have opposite number of atoms to their charges. So looking over at their formula, y is a -3, x gets 3, x is a 1, y gets a 1. So it's kind of a tip to help you guys figure out the formulas based off of the charges. And so writing these formulas, we use the name of the cation. So we don't do anything crazy with cations, because cations are just named after the element. We don't add any prefixes, suffixes, or anything. But if it has more than one possible charge, we're going to denote the charge using Roman numerals. And so what this means is, if we pull up the periodic table, the elements that are in group 1 and group 2, those charges will not change. Group 1, which is in purple, will always have a +1 charge because they're 1 valence electron away from being a stable octet. Where group 2, which has 2 valence electrons, they're 2 electrons away, so they'll always have a +2 charge. But when you start getting into the transition metals and these metals here, they can have variable charges. So you will be getting on your test in the packet that periodic table, it has typical charges. So if it lists more than one charge, you know you're going to have to name it using a Roman numeral. But just for a general guideline, it'll likely consist of these elements. Okay? So, once you do that, I'll move this table out of the way. Then we'll use the name of the anion. Remembering, before I get there, but another way to think of it is name your positive one first, name your negative one second. But talking about using the name of the anion, what I want to go through quick is at the back of this packet that you have, is there's common anion names. So these are the common names for the nonmetals in the upper right periodic table. This is what I expect you guys to know. These are the common ones that we will be using. And so I wanted to give you guys some place you can refer to that lists them in one spot so you can come back and look at it. So C, carbon, its negative is carbide. Nitrogen is nitride. Oxygen is oxide. Fluorine is fluoride. Phosphorus is phosphide. Sulfur is sulfide. Chlorine is chloride. Bromine is bromide. Iodine is iodide. Okay? And so now, switching back, we're moving on to this page here. So I'll move this out of the way for now. So let's use some examples. Oh, actually, we do want the periodic table. 1 second here. So if we're looking at calcium chloride, how can we, potassium chloride, if we're naming it, we base it off of the positive and the negative ion. How do we figure that out? How do we know which is positive and negative? So you can, one, figure it out because the leftmost or the first element is going to be positive, the rightmost will be negative. But it's also good to double check that we know how to get their charges if need be. So if we are looking at the periodic table, if we find potassium, I feel like there's no good color to really emphasize. Let's try this one. Oh, that's not any better. This one. Okay, we're looking at potassium here. Now, it's in group 1, which means that it's going to have 1 valence electron, which means it's going to form positive 1 charge. Now let's look at chlorine. Chlorine is all the way over here in group 17. So in group 17, it has 7 valence electrons, meaning it's going to want to gain 1 electron to hop on over to the noble gases. The gaining of 1 electron, the gaining of that negative charge, gives chlorine that negative 1 charge, which makes it our anion. Don't forget that we just went over typical anion names, and we've talked about them in the previous section, but when it comes negative, you add "-ide". So this is how we get potassium chloride, okay? Now, let's look at iron and 2 bromines here. How would we name it? Besides recognizing what elements they are, now, iron, which is located here on the table, is a transition metal. This means we don't know what its charge is. We have to figure it out. And so when I'm figuring out charges, I like to base it off of our anion, because those are typically always known. And so in our case, our anion is bromine. So let's look at the periodic table. Well, bromine is just under chlorine. That means it's still in group 7. Group 17, it has 7 valence electrons, and it's going to want to form a negative 1 ion. So now we have Br minus 1. So that's the first step, determining that. Well, now, if we look at the formula, it takes 2 of them for every 1 iron. So remembering the fact that we want our charges to add up to 0, for every 1 iron, we have 2 bromines with a negative 1 charge. So the overall contribution of charge from bromine is minus 2. So what does iron have to be in order for the charge to be 0? Well, it must be iron plus 2. So now we know that when we write it, we write iron, we denote the atom's charge with the Roman numerals, and then bromide. Now, if we go to erase this and move this away. Let's look at this example here with Cr2O3. Oops. So again, I always want to start with what is not changing, which is going to be the charge of oxygen in our case, our anion. So if we look at oxygen, let's figure out what its charge is typically. So you look at the periodic table. Well, oxygen sits right here in group 16. Group 16 has 6 valence electrons, which means it's 2 electrons away from being a noble gas. So its charge is going to be minus 2 because it gains those 2 electrons. So if we have oxygen minus 2, now we have 3 of those. So 3 times negative 2 charge, that gives us a negative 6. That's the overall contribution from the oxygens. So now we have to figure out what chromium offers. And so since we have 2 atoms, we have a 2 here, and let's put our x. We're literally solving an algebra equation because we know it has to equal 0. So 2 times what is equal to negative 6? In our case, it's going to be positive 3. And so when we write it, we write chromium. And now these parentheses with its charge is per atom. So we don't write chromium 6. We're writing it per atom. So each chromium atom has a plus 3 charge and then oxide. So what I want you to do right now, and obviously you may not know all the elements quite yet, but I want you to write the names of the following chemical formulas. If you have to look up what the names are of the elements, that's totally fine at this point. But look up the names and practice writing the chemical formulas for these next 4 compounds. So you should have attempted to write the formulas. And so how I would have done it is recognize first that we have all of our positively charged ones at the front. So we'll start by naming those first. Ca is calcium. And because calcium is not a transition metal, it lives in one of the first 2 groups. I know that it can't have multiple charges, so it does not need Roman numerals. Now, fluorine is just going to be fluoride because it's negatively charged. So, calcium fluoride. Mg is magnesium. Magnesium also lives in one of the first 2 groups here, meaning its charge isn't going to change, so you do not need Roman numerals. And then we have sulfur, which becomes sulfide when it is a negative ion. Okay, so our next one then is copper and oxygen. So here we're going to have to determine the charge because copper is a transition metal. So we are going to have to use Roman numerals to denote its charge. So we have to figure out what its charge is first. And so I always start with the anion, oxygen. We already determined before that oxygen likes to take a 2- charge because it has 6 valence electrons and wants to gain 2 electrons to become a stable octet. And so for every -2 charge, we have 2 coppers. What does the charge of copper have to be then? You should have said +1. And so how we'd write it is copper 1 oxide. And then the last one here, again, Fe, or iron, is a transition metal. So we're going to have to denote its charge, which means we have to figure it out. And so we know from before that chlorine likes to take a -1 charge. Well, we have 2 of them, so the overall contribution is -2 from chlorine. So that must mean iron has to be +2. So then we have iron to chloride. Okay. Now, we also have to be able to go from naming them to getting the formula. So what's important to note here is that you have to be able to determine the charge from knowing what the element is. So when I say potassium, you'll have to know that K forms a +1 charge. And sulfide is sulfur's negative anion, which likes to form a -2 charge. So when determining the formula, you have to know how many atoms it'll take to cancel out. So in our case, since sulfur has a -2 charge, it's going to take 2 potassiums to get to +2. Therefore, an overall neutral charge. So that's how we get K2S. Again, remembering the trick that the charge for one is the number of atoms for the other. So keep that in mind. It's a helpful tip. Then when looking at transition metals, their charges are stated for you. So this is pretty nice. So we know that cobalt, or CO, is 2+. Oxygen, we know is 2-. So we just get COO. Versus if we drop down, now we have a 3+ cobalt with a -2 oxygen. So this is where we do the swaparoo of charges. So cobalt has 3, so we have 3 oxygens. Oxygen has -2, so we have 2 cobalts. Now, one thing I want to note, I do this a lot. It's typically in science where we write our charges, for whatever reason, as the number and then negative. So I will switch back in between oxygen 2- and oxygen -2, but it means the exact same thing. But don't get tripped up versus if I write it that way. Same goes for positive. If I write magnesium 2 plus, that's the same thing as magnesium plus 2. So just don't get tripped up by that. I want you to practice writing the formulas from the following names now. So take a moment to pause, try on your own, and then start the video again. Okay, so you should have tried to write the formulas from the following names. What you should have gotten first is if I write the formulas, we have Be and O. Now I have to determine the charges. Well, we know that oxygen likes to make a -2. Beryllium is in the second group, so it makes a +2. That means we just need one of each. BeO. Magnesium is Mg. Phosphide is P. And so magnesium is in group 2, +2. Phosphorus has 3 valence electrons in its group, meaning 5 valence electrons in a group, meaning it wants to gain 3 valence electrons, and gaining -3 charge. Here's where we swap the numbers or make them both equal to 6. So we have 3 magnesiums and 2 phosphorus. Aluminum is Al, and it makes a +3 charge because it has 3 valence electrons. Fluorine is -1. So if we flip-flop the charges for the amount of atoms, we get 1 aluminum for every 3 fluorine. And last but not least, we have cobalt-3 iodide. So cobalt-3 means it's a cobalt with a 3+ charge. Iodide always has -1. And so we are going to need, for every 1 cobalt, 3 iodine. Okay, so moving on to the next page here. Then we need to talk about ternary compounds. And so we'll start talking about polyatomic ions. And lucky for you guys, hopefully it won't be too hard as I'm not going to make you memorize them. But first, let's define some terms. So a ternary compound is just an ionic compound containing at least one polyatomic ion. Oh my gosh, I cannot spell today. Okay, so what's a polyatomic ion? So if we just look at the word poly, which means many or multiple, and atomic, think of it as atom. So it's just going to have multiple atoms. And these atoms are going to stick together like a group of buddies, and they're going to produce some sort of charge. And so the definition I want you to write down is just that it's an ion made of 2 or more atoms. And I think that's enough of a description. Okay. And so there's 4 things that I want you to notice. So here's table E. Like I just stated earlier, you will not have to memorize these. I will be giving you this table for your tests. And so don't sweat about this crazy table of things you see. I do want to point out some things. So they're made up of, all of them are made up of more than one atom. Almost every single one of them have a negative charge. Almost all of them also contain oxygen. And then for those that are positively charged, they have a suffix of -ium, while the negatively charged ones end in -ide, -ite, or -ate. So those are the suffixes there. So I just will point out that we have hydronium and ammonium are positive ions ending in -ium. And so another thing I want to point out about this table is that so I'll talk more about those suffixes here. The 2 atoms. So if it has 2 atoms, it's going to have -ide. So for example, we have cyanide, We have hydroxide, peroxide, now as you have fewer oxygens, that's when you get ite. For example, nitrite, chlorite. So the fewer number of oxygens. Now, you can also have the prefix hypo, which is even less than ite. So you can have chlorite, and then you can have hypochlorite, which is even less. When we switch gears to the other way, when we have more oxygens, then we get ate, like nitrate or chlorate. And so we can also take it further, adding a prefix per, which is more than 8. So chlorate and perchlorate. So these are a good example of the suffixes and prefixes here. And so when we are writing these formulas, for example, when we'd have like an XY2, in our case, when we have to write some sort of polyatomic ion, let's call our polyatomic ion YZ, if we have to write that we have 2 of them, we'll go X parenthesis YZ because they stick together, and then at 2 or whatever number multiple we have to denote it by. So that being said, let's say we had polyatomic YZ and there's only one of them. Just write XYZ. You don't need parentheses unless you have 2 or more. And so looking at some examples, if we look at ammonium sulfide, ammonium is our NH4 sulfides are S-2. Notice how we have parentheses, 2, and then S, because we need 2 ammoniums because they're only +1 to cancel out the -2. But like I said, like silver nitrate or nitrite at the bottom, there are no parentheses because you only need 1 of them. So what I expect you to do is for this next table here is you're going from the names and writing the formula. So for example, for the first one, calcium, you still write calcium the same. Now for chromate, you need to come to this table and look, okay, where's chromate on the table? Here it is. So now the formula you need is CrO4 2-. Well, what is calcium's charge? It is +2. So you only need 1 chromate. And so since those charges cancel out, you just have CaCrO4. So again, the goal here is to try to make a neutral compound. You just need to look up the polyatomic ions, determine their charge, and determine how many of each you need to cancel out to get 0. So try these ones on your own. Pause the video and come back. Okay, so hopefully that went decent. So I'm going to start with aluminum, which is Al. It makes a 3+ charge. And then if you look up sulfate on the table, sulfate lives right here, and we get SO4 2-. So the charges do not cancel out, but we can again multiply each other by the opposition's charges. So we get 2 aluminum, and now I'm going to use parenthesis SO4, then 3. Potassium, that is K. It has a +1 charge. We look up chlorate. Chlorate is, I'm going to switch colors here, this one here. So we get ClO3-. Those charges just cancel each other out, so all we write is KClO3. And then lastly, copper 2 nitrate. Copper, so that's Cu, and since it's copper 2, it's copper 2+. If we look up nitrite, right here on the table, it is NO2-. So in our case, we need more negative charge, so we're going to have to multiply that nitrite by 2. And we get Cu, parenthesis, NO2, 2. Okay? And then, of course, we also have to know how to go back again. Go from formulas to naming. And so from here, what you're going to be doing is looking up these compounds on the table. And so you will just name the polyatomic ion by their name. So we have nitrate, sulfate, and you are also just naming your cation, potassium, zinc by their name. And so when we start getting to transition metals like this third one here, it again turns into a puzzle to figure out the charge of the transition metal. And so the charges for your polyatomic ion, those are set. So always start with those. And so NO2 has a -1 charge. Since you have 2 of them, its overall contribution is -2, which means iron has to be +2. So then we write it as iron 2 nitrite. So I want you to try these problems here on your own. Read through the examples if you want to a little bit more. Pause, try these, and then come back. Okay, first one. So we break it down. Al, that's aluminum. NO3, go to the table and we look. That's nitrate here. So once we find that it's nitrate, it's just called aluminum nitrate. Next, we have calcium. And now we look up what MnO4 is. According to our table, that is permanganate. So we have calcium permanganate. Now this one, since we have cobalt, which is a transition metal, we need to figure out what's going to go in its parentheses for its charge. So we first look up carbonate. Right here, its charge is 2-. So if carbonate has a -2 charge, and there's 3 of them, that totals a -6 charge. And then we need to get to -6 from 2 cobalt, or sorry, +6 from 2 cobalts to equal 0. That means cobalt has to be charged +3. And then we write carbonate. And last but not least, what I put here are actually 2 separate polyatomic ions. So NH4 is ammonium, and OH is hydroxide. And then your last page here is what we already gone through, so we are ending our notes there.